Hi. We have to compare two version numbers. Each version number has three parts, and then we have to answer whether the left one is an earlier version, the same version, or a later version than the right one. So let's have an example here. 1, 2, 3, and 1, 3, 2. Now, as a human, I can immediately see that the one on the right is the newer one. But it's actually a little bit involved what's happening here, because I must be scanning from the beginning to see what the first part is that differs. So the first one is irrelevant, they're the same. Only the second part is important, and that means that the third part isn't important. The fact that this one has a higher number here, this one over here has a lower number, doesn't matter because an earlier number is more important. So let's make a tacit solution to this. We need to compare corresponding elements, and the comparison of size that we can do with a subtraction. And so here we can see that this part is an earlier number than this part, and this one is a later number than this one. That corresponds to the negative 1 and 1 here, and then the first digit, the first number is the same. That's where we get a 0. We're not actually interested in the difference itself. So let's say that over here we had a 4. Then we had a difference of 2. And we're not actually interested in the zeros either. So what we can do is we can remove the zeros. So we can use a set difference with 0. And because we are doing everything in a functional style, everything in terms of functions, we have to mark this 0 as being a constant function. So this 0 is actually a function, 0 with this symbol. To the rest is actually a function that takes these two arguments and evaluates to 0. And then we use that with set subtraction from the differences between these numbers and these numbers. And that gives us negative 1, 2. So we've gotten rid of one part that we're not interested in. Second part we're not interested in is the actual magnitude of the differences. We only want to know which one it is. So we use the multiplication symbol with only one argument, that is the signum, the sign, and that will convert any number that's larger than in magnitude than 1, so 1 or anything beyond 1 or negative 1 or 0, it leaves them down at 1 or negative 1 or 0. And finally, we want to prioritize the first difference, right? Anything that is the same, we already eliminated with removing the zeros. But we want the first one, so we have a first function that we glue together with the signum function. So this is a new function that we have composed, and we're applying that to the result of this set difference between the subtraction and the 0. And that gives us negative 1. But we can actually do this in a little bit different way as well, that I think is really cleverly thought out. Let's go back to the difference between these version numbers. And we are not interested in the magnitude, so we apply this time the signum function glued together, composed with this difference. And instead of trying to eliminate the zeros and then finding the first one, then we can evaluate this in base 2 as a binary number. Now, if the magnitude if there were multiple differences, then this could be a larger number. We can take an example of that. So let's backtrack a moment and do 625 over here and 713 over here. So now we have two differences over here where the left one is larger and one where the left one is smaller. And now we evaluate this in binary, and we get um, -1 because this, and this is a bit interesting what's happening here, because I'm saying I'm evaluating in as binary, but normally you're used to binary being only digits 0 and 1. But here we also have -1s. So what does this mean? Well, it's actually really not that complicated. What's happening is we have these numbers, and they are just values for the digit positions. So the digit positions in a binary system with 3 bits, so to say bits, they're not really bits because they could be -1. Well, the first one is 4, the second one is 2, and the third one is 1. The last one is 1. So we could multiply that. That gives us our total amount. And then we just need to sum it all up to get the final result. So we can add a plus reduction here in the front, and that gives us -1. Of course, if we had the same value at the end, then we would get something with a larger magnitude. So uh, we at the very end we need to again take the signum, the sign, because we don't want a larger number than -1, or larger in magnitude than -1 and 1. And let's go back to how we actually spell that. So this is the binary evaluation of that, and then we can take the signum of that for the actual solution. And yeah, this seems clever, but do we really understand what's going on here? It works. But why is it that it works? Let's go back to this example we had before with 6, 2, 5, and think about it for a moment. Here, we have basically the worst case possible. What we should be afraid of is that maybe a lot of trailing numbers that are greater here on the left, but smaller on the right, would weigh out, they would add up to so much that even though the first number is smaller than the first one on the right, it would still overweigh it. So we would consider this to be a larger number. What if we had a lot of huge numbers on the left and a lot of smaller numbers on the right? And the important thing here to understand is that the binary system is exactly this. Okay? It has the property that if you add up all the fully set bits and trailing bits, then they add up to exactly one less than the next larger bit. Well, that's nice. We know that about a normal binary system, but what about when we have these negative numbers? Well, that can never make it any worse, because if we have any zeros on negative ones here, of course that adds up to even less. And over here, we the negative value here is, well, in magnitude larger than the sum of anything that could be here. So it all works out to evaluate in binary, even though it's not actually true bits, it can also be negative, and then we take the sign of that, and we get the correct result. Thank you for watching.